quite a title, quite a lot of stuff, quite a cave in the uplands of Kerr County on a family ranch that's been owned by that family since 1918. A family that has been incredible stewards of the science that's in the cave, and for decades have allowed multidisciplines of scientists into the cave to do studies in which dozens of publications have been made on it. This is more, if you came to listen to an archaeology lecture, there'll be a little bit, but this is going to be a lot more about a lot of other things that you see on that title. But before I go any further, I want to introduce the Hall family. They're our special guests tonight, and I'm going to introduce them, and I want you to hold your applause. But when I'm finished, these people deserve a lot of praise. They are so open, and this data, and you'll just see some of it tonight, is it's literally world famous. And a lot of you have probably never heard of it. So first of all, I'd like to introduce Tommy and Debbie Hall. And you guys are going to have to stand up, okay? It's Tommy and Debbie, and Lee and Fran, and Susan Hall Story, and Travis. So let's give them a big hand. Thank you guys so much on behalf of the scientific people for all that you've done. And I got to tell you one little quick story before we get into the presentation. I've given several presentations on Hall's Cave around here. The first one was in 2017. I didn't know the Hall family at that time. I did, however, know Dr. Ernest Mendias, who is a retired emeritus professor of vertebrate paleontology at the University of Texas, Austin, who is about 93 now. He's still kicking. And he and I have known each other for some time, and that's the connection I made with Hall Cave, because he was one of the very first scientists in that cave in the 1960s. So I got a fair amount of information from him, and then literally I just mined the literature that was out there to put this presentation together. Gave the presentation in the summer, I think, of 2017 down at Riverside Nature Center here, where a lot of public presentations are given. And I go through the whole presentation, and we get through, and I ask the questions. I get a few questions. I see this hand in the back, somebody I don't know. And I think I motioned. I can't remember exactly the sequence. I think I motioned to him, and he stood up, and he said, "My name's Tommy Hall." Things raced through my mind. I thought, oh my gosh, did I say anything wrong in the presentation? I didn't give away where the cave is, the confidentiality of it. Just things were zipping through my mind. I finally composed myself, all of this in a split second or two. And I said, well, Tommy, I think this is very good to meet you. And I think Debbie was with you. And I said, very good to meet you. I wish I could have met you under earlier circumstances, but at least here we are now. And I said, I was particularly worried, thinking back of what I might have said, so trespassers might not find out where your place is. And he very confidently said, I don't have to worry about trespassers because I carry a 45 caliber. And later I found out he was a deputy sheriff. So. All right, let's get into this. Now, I don't know if you folks in the back can see these slides, but I would encourage you to come forward because the light is not going to get any better in the next 30 to 45 minutes, which is about what the presentation is going to be. Like I said, first investigation is 1960s, and that was literally the father of this group of halls I just introduced you. And they have carried on that tradition. The cave itself is not anything unusual. It's a typical karstic cavern in the Edwards limestone. There are a lot of them in central Texas. Doesn't have a particularly large stalactites or anything like that. But it's not the shape and size of the cave. It's what's in the cave, in the sediments of the cave, that make it so important. That data has been used to make interpretations and record ancient assemblages of animals and plants throughout the last 20,000 years. Also to reconstruct soil depths, which are extremely important in reconstructing what the floral ecosystem looked like. And particularly to reconstruct ancient climates, all the way 20,000 years back. It was recorded as an archaeological site in 1991, I think, 41 KR7, 41 KR 474. And this is a quote from this same Ernest Lindelius, who was a highly respected vertebrate paleontologist. He was a Pleistocene mammal expert. So he was all over the caves in Texas, looking at Pleistocene vertebrate faunas. That's a quote, literally, from him to me. He says it's not only the most significant cave in Texas for this kind of data, it's one of probably the top 5 in North America, and certainly ranks up there in probably the top 10 in the whole world. Right here in little old Kerr County. This is what it looks like. It is uniquely positioned. If you can see that laser, that's the cave mouth. And you can see there's a slope. And what you can't see is what's out here, but it's even better slope. The uniqueness of it is the slope and the soils that were on the slope throughout the millennia in flood events drained into the cave. It's like a funnel right into the cave. And everything that was in the soil, dead plants, dead animals, wound up in the cave sediments. Things were brought into the cave by predators. They wound up in the sediments also. Other animals lived in the cave. When they died, they were covered by the sediments. And that's the uniqueness of it. It's got an almost uninterrupted 20,000 years of sedimentary deposits. These are just some of the publications. They go back to the 60s and are as recent as just last year. And there's some in press now. And I'd like to really stop at this point and thank some of the ones that really helped me with this, starting with Dr. Lindelius several years ago. But most recently, Dr. Thomas Stafford, I know who some of you know, who has done a lot of work in the cave over the last several years, since I think 2017, when the last round of the Texas A&M work began. And along with him, also Dr. Michael Waters from Texas A&M, and Dr. Joshua Keene from Baylor University. And the last time I was out there, which was maybe 2.5, 3 weeks ago, Dr. Keene was still there with his students. And I know there's one of them here. Spencer, raise your hand. Are there any others here? No, you're it. Okay. By the way, Spencer does play the guitar and works small gigs if you need something. I think he's very cheap. Okay, so it's got good press. I mean, it's really highly endorsed. All right, so this is what I was talking about. You look at other Texas caves, you probably can't see them, but that's Friesenheim Cave. I think most of you are familiar with that. These black bars represent the time periods which sediments age date in the various caves. I put a green bar here just to make it a little plainer, but Hall's Cave is uninterrupted right out to here. Now this is in radiocarbon years before present, so it's not 20,000, but when you calibrate it to calendrical years, it's 20,000, right at 20,000 years before present of continuous sedimentation. Now a little bit busy, but just to show you the Pleistocene epoch here, out here at almost 2.6 million years to the Holocene, beginning of the Holocene, 11,700. Follow this chart down to here. Holocene epoch here. This is the sediment package of Hall's Cave here. 20,000. And these dates here, 15,500. There are 2 sites in Texas which have now been fairly well recognized as credible sites where humans did live, and that's at the Galt site and the Deadwood Freakin site, which are basically one site. They're just contiguous to one another and worked by different groups. You can see the last glacial maximum up there is ending about 14,700, and that's the Holocene epoch right there. And then that bar there represents the culture in Hall's Cave, which dates back about 10,500 so far. Now, investigations will go on at some point in Hall's Cave, but probably the field work is done. Am I pretty much right about that sense of far time?
Yeah, for now we're planning to go. Hopefully, go back to we got about 30.
All right. Now, very hard to see, but I just wanted, this is one of the slides that Dr. Keene provided for me. It's very difficult to see, but that's the cave floor. This is down towards the base of the cave, sediments, and there's a calibrated date there, 19,910 to 19,910 to 19,293. And that's the main chamber of the cave. That's the first thing you see when you walk down a ramp into the cave, dodging the rattlesnakes as you go in. No, we didn't see any rattlesnakes, but Tommy warned me about it the first time he took me there. Some other shots in the cave. That's actually 2018. That's Dr. Waters standing there. Some of the main excavation area there. Are you guys able to see this green laser? More or less? Okay. And I know you can't see all of this, but I put it up there to show you the detail that Tom Stafford's stratigraphy looks like. He's not only a noted stratigrapher, but he's also a chronologist. He's got his own radiocarbon lab, and basically world renowned. All right, so we're going to talk about the archaeology first. Then we're going to move into vertebrate paleontology. Then we'll move into other aspects of what the cave yields. As far as the archaeology, I already mentioned when it was first recorded. And in those early days of the archaeology there were some burn rock middens that were noted outside the cave on the ground surface, and diagnostics over the ground on the surface. Basically, the oldest point they found was an Angostura, which is the very latest, late Paleontology, and the youngest was Austin phase, I think, maybe Edwards airports or Scallon airports. And within the cave, about that time, up to 1994, there were some hearths, some fire hearths reported. Basically charcoal hearths within the sediment of the cave, but only down to a meter. Now, in 2017, Texas A&M and a group of other scientists, I'll just call it the consortium, began this latest phase of investigation within the cave. And those are some of the charcoal hearths. So those black lenses there in the wall. I believe they've obtained about 72 dates all total within the hearths or within other parts of the sediment. And I'm not sure if it was 50 hearths or not. Spencer, do you remember?
It was about 60.
60? 60 hearths. Okay. Now, when I was talking to Joshua Keene a couple of weeks ago, he said when we would dig into these charcoal hearths, you could literally smell the smoke still, smoky, sooty smell, because it's so well preserved in that dry cave setting. With this latest work, this latest archaeological work, they've identified at least 10 separate occupations of the cave, starting back at 10,500 cal BP, about 250-year period, all the way through the Archaic and ending up in the what looks like a 700-year occupation period between 1,500 and 800 calibrated BP. And within that, there is a small burn rock movement. Might be more, but I know of one. Within those occupations, they can identify 3 of the 4 major periods of buffalo abundance in central Texas and buffalo hunting, and those are the basically the Bell Andice time of 59-55 to 58-15. I mean, that's 140 years. It's not very long, but they've got evidence in there of that and dated to the horse. You know, the Pedernales points associated with the 3290 to 3130 cal BP, and then the late Archaic Castroville, Montel point assemblage and Marcos points. They do not have the representation of the Toya phase, so these points, which was a big buffalo hunting period. But in the cave, in the sediments, they do have a good Angostura, a late Paleo, and then the significance of all of these points, and there's a lot of them, all up and down this sequence, with the horse and with the dates, is they're so closely associated. They give so much information about the temporal spans of these different forms, and it really adds to Texas archaeology to have that. Now this is the last thing I'm going to show you about the archaeology, and then we're going to get into a bit. I knew that would happen if I knew it. This is Michael Collins' work from 1995. And what he did was to calculate from the various sites in central Texas the buffalo remains and get dates in those sites of when those buffalo remains were there. So what you're looking at here are 4 big brown bumps which represent buffalo abundance. That's not to say in these intermediate areas that they weren't buffalo in central Texas. It just means they were at least much more sparse than these 4 blocks. Okay. Now, let's talk a little bit about the vertebrate paleontology. I'm just going to have to hold on because I'm going to bring all this together a little bit later, but I'm going to present different data sets, basically independent of one another, which I think you'll be able to see are telling pretty much the same story. So this was the first Burt Paleo work. It was under the guidance of Dr. Ernie Lindelius. It was Dr. Rickard Toomey III, and he did a lot of excavation in that cave. And this is some of it, just some of it. The extinct fauna that he found were a small camel, the giant buffalo, bison, and tegus, but no skull or no teeth, just limb bones. A dire wolf, which is a much bigger version of our modern gray wolf, and 2 species of horse. These are all Pleistocene horses, so it wasn't a modern Equus caballus. It was an Equus, I can't think of the species name, but it was 2 separate species. And then these are all the large fauna. The modern mountain lion, which we still have around. The North American jaguar, which is very rare in North America. In the United States, there are some along the Arizona border, but not in this country anymore. Pronghorn antelope haven't been here for a long time, but they were. The modern buffalo bison hasn't been here for a long time, but they were. They're not extinct. They're just not in this geographic range anymore. The gray wolf is not in this geographic range anymore. And those little critters at the bottom, prairie dogs, moles, pocket gophers, and so forth, were plentiful, but have generally become not extinct, but they're not in the area anymore. And it all has to do with the soil depth, which we will cover a little bit later in the presentation. Now, the latest paleo that's been done in the cave under the consortium since 2017. One of those is basically a DNA analysis, not only of the bony material in the cave, from Toomey's earlier excavations and the consortium's excavation since 2017, but also with the soil itself, because in the soil are the remains of animal urine and feces and hair, all of which can be DNA type. And so that has basically come very close to what Toomey had already just by visual vertebrate paleontology identifications many, many years earlier. But also, they found 45 taxa of plants, 45 different plant taxa, which Toomey had not focused on. He strictly focused on fauna. And within the consortium years of 17 to present, the most famous saber-toothed cat that you know of, called saber-toothed tigers or saber-toothed cats, Smilodon fatalis, genus species, has been found in the cave. Now there's another big cat that was contemporaneous with this big Smilodon, which Smilodons, by the way, are about the size of a modern African male lion. But there's another type of big cat that was contemporaneous called Homotherium, genus Homotherium, which had shorter canines, and they call it a scimitar cat. That's what you usually find in Texas caves when you find fluid remains, but there's no Homotherium in this cave. They're all Smilodons. Now, there was a bison antiquus complete skull found in 2017 and then removed in 2018. I guess it's the DNA, but I'm not certain, confirmed the existence of the extinct short-faced bear. Now, this was a huge animal, like 12 feet when it stood up on its hind legs. A formidable foe in that time. There's a picture of Mr. Lee Hall when they were first uncovering the bison antiquus skull. That's a cast of the skull. Picture I snapped at Lee and Friend's house one night. They've got a miniature cast of it, but it basically by the shape of the dentition, the wear pattern on the dentition, it appears to be a mature animal, but certainly not an older. Much older. It's definitely not a younger family. Now, this is where I really think it gets good. This is Tom Stafford, and he's pointing to a scapula which was associated with that bison skull. That's the scapula. That's the bison scapula. There were ribs associated with the scapula. The rib. Then there's this, which was right underneath the scapula. That is a humerus of Smilodon fatalis, this bone in the leg. Now, how does that get underneath the bison antiquus? That must have been an interesting story to see how that developed, because it was basically in contact with it. That is one of 3 Smilodons that they found in the cave. I think this one was about 17,000. The other 2 were roughly 15,000 and 13,000. But that's an unusual amount of Smilodons in Texas. If you forgot what they look like, that's what they look like. As far as the coloration, we don't know. But that's a soft tissue reconstruction, and it was a big cat, and everybody's heard about that from the time you were a kid, I think. But really, as interesting as those big animals were, and that's just a few of them, the most interesting ones that provide a lot of data are the small ones that are really sensitive to environmental changes. They're sensitive to live in narrow environmental windows, like a certain hotness or warmth or cold, wetness or dry. And because of that, they are used as proxies. I'm sure a lot of you know what that means, but it's basically this. Let me give you an example. If you've got a species A, let's call it, that is present, that we have today, and we know that that species A lives in a certain climate zone. It can exist within a temperature range and within a wetness dryness range. And we find that specimen A in Hall's Cave a meter down. Then we can basically say, along with a lot of other small mammals, proxies, we can say that zone at a meter, for instance, had a climate basically like the climate we have today. So that's the proxy approach. And when you've got the stratigraphy dated, which they got dated very well in this cave, and they put all those proxies in there, then they can start to predict what ancient climates were. Right, so we're going to build on this graph with the buffalo abundance, and what you see here is wetness versus dryness. So the wetness in blue, the dryness in yellow, and this is from Collins 1995, where he took Toomey's findings and made paleoclimate predictions. Do you see some correlation there? Buffalo are going to thrive on abundant grass. Abundant grass is going to be there because it's wet, not dry. It's real easy to correlate that dry period with lack of buffalo, that wetter period with that with that. The only thing that doesn't really correlate is this would be Toya phase. And what I did here, because Collins stopped here about 13,000 years, what I did was to take the same methodology and extrapolate it out here using Toomey's conclusions, but putting it in graphic form, and so that you can see wet, dry periods. Okay, now let's talk about the plants. These are the phytoliths. Phytoliths are little silica particles that are in the micron size, you can't see with the naked eye. They are produced during plant photosynthesis. The plants are going to be in the soil is going to have some silica in it. It's going to be taken into the plant during photosynthesis as the plant is ingesting CO2 and then making oxygen and expelling the oxygen in the atmosphere. And when the phytolith forms, it will form according to what kind of plant made it. In other words, what photosynthetic plant was making that phytolith. So they can be used to identify what plants were there. You rarely can get down to the specific level of grasses, but you can certainly get down to the family level. So in the taxonomy classification here, family, genus, and species. So just to get to the family is doing pretty good with phytoliths. But there have been 2 phytolith studies done. The 2011 one by Joins, and then the most recent one by Cordova and Johnson, and they also use pollen. All right, let's plot those up there. We're going to put Joins graph here below these two. So this is a moisture diagram graph here on the top. This is temperature here. We won't cover that one just yet. But you can see also a correlation. Here's a more moist period, which correlates with that, which correlates with more buffalo, and so forth, right on over. Bringing pollen into it, some of the first studies were done by Brett Alsman in 1993. Collins again took that data and graphically portrayed it in this graph down here. Again, line up wetness, dryness, a little wetter, dry, wet, all lining up. Okay, now this is a 2020 publication by Sears Home, sorry. And what it is, this graph here is basically the temperature on this graph. I don't have numbers because it's a relative temperature. That graph is constructed from ice cores. And the value of ice cores, of course, you don't have ice cores in Texas, but you have ice cores in the Greenland ice sheet, you have ice cores in Antarctica. And literally, some of these ice cores are 2 miles long. In other words, they've drilled down through the ice 2 miles and recovered the ice core. And so, why? What do you get out of that? Well, when snow falls, when that ancient snow fell, it trapped atmospheric air and it compacted as ice and was buried deeper and deeper and deeper. Those little air bubbles, which were ancient atmospheres, are trapped in the ice cores. And by knowing how modern amounts of CO2 and oxygen, isotopes of oxygen, O16, O18 occur relative to each other, scientists can take these ancient ice cores and analyze those components and predict what the temperature is then. And in case of ice cores, several 100,000 years ago could be predicted. So what I'm showing here is how all this lines up with all of this. And so this is cool. It gets warmer here. That's the end of the last glacial maximum right there. Bowling out there, Younger Dryas, basically a rapid cooling there, and then it begins to warm up in the Holocene. Just hoping the screen doesn't go away. All right, now that red dashed bar that you just saw there, that I superimposed on it, out of Sears Home et al. 2020, that's where that red bar would go for temperatures during the last glacial maximum up till 14,700 years ago in this country right here. So it was about 50 degrees Fahrenheit annual mean here, 20,000 years ago to 14,700 years ago. Well, that's a 15-degree temperature difference from what we have now. We have about a 65-degree average per year, annual mean temperature per year. Now, 15 degrees is a lot. Let me give you a comparison. In today's climate, it would be like living at the border between the U.S. and Canada. That's how cold it was here during the last glacial maximum. We didn't have any of the glaciers, but we certainly did have the cold. It's thunderstorm sort of getting up, huh? Okay. Maybe I should talk faster. Okay, so there's the 50 degrees, and all right, we'll come back to that. I want to talk a little bit about soil depth now, because there's a whole other set of studies, principally done by a lady named Jennifer Cook in several different publications. The soils in this area in central Texas now are much thinner than they were in the Pleistocene, even 8,000 years ago. And they built up. Get back.
Sorry about that. I think it's going to get us here.
Jay, I'll give you the punchline, okay? The punchline at the end, one of the last things they found out is in the Younger Dryas sediments. Somebody occupy Jack's attention, okay? Yeah, there we go. In the Younger Dryas sediments in the cave, they have identified, I get this, never heard this term before, cryptotephra. You like that? It's a fancy word for volcanic debris, volcanic ash. There are several theories about why after this warming, after the last glacial maximum, did it suddenly begin getting much cooler again, as cool as it had been during the last glacial maximum. And there are several theories. One of them is it was a comet impact. What they found in the cave indicates it was not extraterrestrial. They found elements, they found osmium, tiny pieces of osmium isotopes, 187, 188, I think, for a chemist. But basically, you don't get that out of asteroids or meteorites. It comes out of the mantle, which suggests volcanic eruptions. Coincidentally, at 12,900, Younger Dryas cooling, there is a huge volcanic caldera lake in Germany called, can't remember the name of it now. We need a slide. Lockersea volcanic caldera, which last eruption was 12,900 years ago. Now it's almost a 2-meter caldera now, but it could have been totally coincidental, or it could have been part of the reason why you've got this cooling effect that was what was happening with the Younger Dryas. The most common theory, by the way, is that that it's this huge glacial lake called Lake Agassiz developed from glacial meltwaters, and it was about 170,000 square miles in size, covered a lot of the Dakotas, Manitoba, British Columbia, and so forth. And at a point, it spilled into the Arctic Sea. It was like a dam breaking. With that influx of cold water into the Arctic and therefore the Atlantic, what happened was the normal warm waters that come up from the Gulf, which regulated the climate, all of a sudden got a cold water dose. And that is the most common theory of why the Younger Dryas happened. The volcanic thing might be part of it, but it's just like the dinosaur extinction with the meteor. The meteor might not have been the only thing that was responsible for the dinosaur extinction. There was volcanic activity in India, which formed the Deccan Flats, which were tens of thousands of square miles of lava that flowed out at 65 million years, coincident with the same time that the meteorites hit the Yucatan Peninsula. With all that lava, you get CO2, you get sulfuric gases, and so forth, just like you would with this Lockersea volcano, although on a smaller scale. Well, I didn't mean to rush through that, but that's it. That's basically it. Yeah, and that's already been published. So that's a recent publication in Sun et al. 2020. Thank you. Thank you. If you got a question, I'm willing to stay.
Yeah, if you've got a tent you need to batten down, it might be a good time to do that. I think that's going to be it.
Put it down and let it do it.
You know, common scale for wet and dry. That's what it is. Really? The graphic. You know,
Anyway,